This is 7-6, choosing a factoring method. When choosing a factoring method, you kind of have to ask yourself some questions. So first you see, is there a GCF among the terms? Then from there you want to decide how many terms are in the polynomial. As you can see, if there are 2 terms, you're going to see if there's a difference of 2 squares. If there are 3 terms, you want to see if it's a perfect square trinomial. If not, you would move on and see if it can be factored into 2 binomials. So that's when you want to see is A 1, does A equal 1, or is A not equal to 1? So which method are you going to do? 2 terms that multiply to C and add to B, or 2 that multiply to AC and add to B? And if there are 4 terms, you're going to factor by grouping. Okay, in example 1, it says, tell whether each expression is completely factored. If not, factor it. So I'm looking at the group of 6x minus 4, that binomial, and I see that I could have actually divided this by 2 as well. So if I do that, then that 2 is going to come outside, and that's going to be multiplication. So you'd have 6x squared, and what's left is 3x minus 2. Now it's factored completely. In example B, I have a couple binomials, so I could see if there's a GCF. There's no GCF here except for 1, so that does me no good. There's no GCF in this group except for 1, so that does me no good as well. And then next I could see if there's a difference of 2 squares. Well, this is a sum of 2 squares, but that is nothing. There's nothing I could do with that. And here, the 4 is a perfect square, but the x squared, the x would need to be squared. And so since it's not, it's already it's fully factored. There's nothing more I can do on that one. Okay, factor by recognizing patterns to make sure we'll factor completely, it says. So what I'm doing first is I always check to see if I have a GCF. So I see that I can divide both of these by 2. And I can also keep the smallest of the common variables. So I see that there's a y common. I'm going to put that as my GCF. So I'm dividing both of these by 2y essentially. And I want to see what's left. So in this first term, the y's cancel and 2 divided by 2 is 1. So we're left with x squared. In the second term, 2 divided by 2 is 1. And y to the third divided by y, we subtract those exponents, leaves me with y squared. Really, it's y times y times y. And on the bottom we had y, so you can cancel one of them. So we end up with y squared. So it's 2y times x squared minus y squared. Next, since there's a binomial here, I'm looking to see, did I factor it completely? Is there possibly a difference of 2 squares? And I notice that there is a difference of 2 squares. So when there's a difference of 2 squares, it's going to have different signs. And I take the square root of x squared, which is x, and the square root of y squared, which is y. Now it's factored completely. Okay, in example B, start with the GCF. So I know I can divide all of these by -2. And the common variable would be x in all of them. So the -2x will go outside. -2 divided by -2. Well, I took the -2 because it's the leading coefficient. I know they're not all negative, but I tend to do that if the leading coefficient is negative. Okay, so the x's cancel, so I have y squared here. For 16 divided by -2, I get -8, and the x's cancel, so -8y. And in the last one, the x's cancel, and negative divided by negative is a positive. 32 divided by 2 is 16. So this is what I'm left with at the moment. And it is a trinomial. It's not, it could be a perfect square trinomial, actually, so let me check that. So the square root of y squared is y, and the square root of 16 is 4. And y times 2 times 4 is 8y, so it is a perfect square trinomial. So therefore, perfect square trinomial will take the operation, the first operation, which is a minus sign, and the y and 4, the square root of the perfect squares, and put a little squared symbol next to it. Okay, in this next example A, I see that I have a trinomial. There's no GCF, so I'm jumping to my trinomial options. Perfect square trinomial, well, this 2 is not a perfect square, so that's out. So then from there, I know that I have A not equal to 1. So I'm going to have to do the AC. So 2 times 4 is 8. I need two things that multiply to 8 that add to 5. My options are 8 and 1, 2 times 4, and that's it. So for that reason, this cannot be factored. Okay, in example B, I see that I can take a 3n squared out of all of these. So I'm going to divide all these by 3n squared. That's my GCF, and I can see what's left. Well, here I'd have n squared for the first one, minus 5n, and last it would be plus 4. And so I could see if I have a perfect square trinomial, n times 4 times 2, it would have to be 8n in there, so that's not going to work. So I have a basic trinomial where a is 1, so I need two things that multiply to 4 and add to negative 5. So I could do 4 and 1 or negative 1 and negative 4, so that's what's going to add to negative 5. And I don't have any squares in there, so I know I'm not going to have any difference of squares. Okay, in example C, I'm going to take out the GCF. It looks like I take out a 2x for all of these. So divide by 2x for all terms. We end up with 2x squared plus 9x. And last is plus 10. That is not a perfect square trinomial, so I'm going to be using the AC method. So 2 times 10 is 20, so I need two terms that multiply to 20 that add to 9x, and that would be 4x, 5x. So now I can rewrite the 2x just gets dropped down. I'm going to drop it down even further, actually. So I can have room here. And then I'm going to be writing my 4 terms, which are 2x squared plus 9x, oops, not 9x, sorry, split the b, so plus 4x plus 5x plus 10. And I'm doing factor by grouping, so I'm going to take the GCF out of the first group, which is going to be a 2x, and that leaves me with x plus 2. In the second group, I could take out a 5, and that leaves me with x plus 2. Well, that's good, because I see my twin, so I'm going to put my GCF here, and my common binomial of x plus 2 there. And so now I can write 2x times 2x plus 5 times x plus 2. And there's nothing small in that because those binomials have been factored completely. And there's no difference of 2 squares. So here this is a binomial. It does not look like difference of 2 squares at the moment. So I can actually start with my GCF, which is what I'm supposed to do. And so get p to the 4th minus 1. Now I see a difference of 2 squares. As long as this is an even number, we just cut it in half. So that's going to become p squared, and the square root of 1 is 1. And then we need different signs, since it's a difference of 2 squares. So now that's factored completely.